Hello Chem 213 students, and welcome back for our third and final lecture of this week. So far we've learned about a number of electrophilic aromatic substitution reactions that can install a variety of groups on a benzene ring. These include the reaction of halogens in the presence of a catalyst such as aluminum tribromide or aluminum trichloride. They include the installation of nitro groups through the use of the nitric acid and sulfuric acid, the installation of a sulfonyl group through fuming sulfuric acid, the Friedel-Crafts alkylation using an alkyl halide and the aluminum trichloride, and the Friedel-Crafts acylation using an acyl group along with aluminum trichloride or iron trichloride as well. And so here we understood the considerations of which positions they might install themselves on, where the groups will be installed when there's already a substituent on the benzene ring. In addition, we can follow these up with a variety of reactions that we've learned previously. So for example, we talked about in this chapter how we can reduce a nitro group to be an amine group through the use of iron and zinc in an acidic environment, followed up by a base to deprotonate the protonated amine group. We also talked about how we can reduce the acyl benzene here by the use of a zinc-mercury amalgam in an acidic environment with heat, and this completely reduces the carbonyl so that it no longer exists and is replaced with 2 hydrogen atoms. In addition, in the last chapter, we learned about how we can do benzylic bromination through the use of NBS to brominate a benzylic position on a carbon attached to a benzene ring. We also learned how we can oxidize an alkyl group on a benzene ring through the use of strong oxidizing agent potassium permanganate with water and heat, followed up with acid to protonate the resulting carboxyl group that is produced here. So these are the kinds of things that we can do synthetically now that we have all of these reactions together. So synthesis of a di-substituted benzene ring, we'll have to consider carefully the activating and deactivating effects of the group and also their ortho, meta, para directing effects. So if we want to install these, for example, here we have a bromine that is meta to a nitro group. If we have a nitro group already installed, we're going to be installing a group in the meta position. If the first group installed should be a meta director if we want to install at the meta position. So for example, bromine here is an ortho para director. The nitro group is a meta director. So if we want to produce this from a benzene ring, we would want to install the nitro group first, because then the installation of the bromo group will be in the meta position here. If we install the bromo group first, the nitro group will be installed at the ortho or para position, which is not what we want. So when we're synthesizing substituted benzene rings that are di-substituted or tri-substituted, we need to consider the activating, deactivating effects, and also the ortho, meta, para direction effects of each of these groups. So this is a summary of how we would think of these considerations here. If we need a meta director, here we would want to install a nitro group. However, if we reduce this nitro group using zinc and hydrochloric acid with sodium hydroxide, as we discussed, we can get an amino group, which is a strong activator and an ortho para director. If we have a carbonyl group here, if we reduce it to an alkyl group, the carbonyl group is going to be here a meta director, but we can reduce it here to an alkyl group, which would make it an ortho para director. Remember, this is a deactivating group due to the resonance with the oxygen. So that's very important to understand. You don't want to memorize this, right? You want to remember why is the carbonyl here, why is the acyl group a meta-director? Well, it's because it's deactivating. All the deactivating groups are meta-directors with the exception of halogens. If we have a methyl group, that is a activator and thus an orthopara-director. All of the activators are orthopara-directors. If we need a meta-director instead, we could oxidize the alkyl group using potassium permanganate and water, followed up by acid to protonate the resulting carboxylic acid. That is going to be a deactivator and thus a meta-director. If we want to produce a meta-director, another option here is to brominate, which by induction would be electron withdrawing and thus would be a meta-director. So we have to consider these reactions and what kind of direction they produce for the installation of a second group. We have to also think when one of the groups requires more than one step to install. We have to think about what would be the result of the subsequent reactions. So here, if we're trying to produce this ring here, well, the amine group is a activator and an orthopara-director. So you would not be able to install the chlorine with the amine already there. But if it's a nitro group, the nitro group's a deactivator and a meta-director. So what we can do to get this product here is we can start by using nitric acid along with sulfuric acid to install the nitro group, which is a deactivator and a meta-director. We can then install the chloro group before we reduce it, right? So if we reduce this here, now it's going to be an orthopara-director, but we want the chlorine at the meta position. So what we should do instead is we should install the chloro group first, and then we should reduce the amine. So that's what we would do here. So instead, we would go, okay, instead of doing this right away, we're going to go over here and we're going to use the Cl2 and AlCl3, and we're going to produce this product right here, and then we'll do this reaction right here, and we'll ultimately reduce the nitro group and produce the final product. And so this would be, first we install the nitro group, then we install the chlorine atom at the meta position, then we reduce the nitro group to an amine, and then we finally have the product that we want. So when we're thinking of synthesis now, we have to not just think of the reactions, we have to think about the ortho-meta-para direction of the reactions. Another thing to think about is that nitration cannot be done in a ring that already contains an amino group. That's just something that will not work here. So if we already have an amino group, we cannot do a nitration, because we would then make this into an amino group and it won't work. So that's one thing to keep in mind when we're doing these syntheses. This cannot be done in a ring that already has an amino group. It can be oxidized here. It's good. The amino group's going to be oxidized with the nitric acid and sulfuric acid, and you'll just get the NO2 back. Other things that we have to think about: the Friedel-Crafts reactions will not work on a ring that is strongly deactivated. So if we have a strong deactivator such as an acyl group, any of these carbonyl groups here, very, very strong deactivators, we're not going to be able to do an installation, we're not going to be able to do an alkylation rather, on this reaction that already has an acyl group. Or if we have a strong deactivator such as NO2, we can't do a Friedel-Crafts alkylation. Okay, so up until now, we've been talking about electrophilic aromatic substitution, where we react the aromatic ring with an electrophile, and the aromatic ring is the nucleophile. We can also do the opposite, where we make the aromatic ring the electrophile, and then react it with a nucleophile. The example here would be hydroxide. So we can substitute an alkyl halide, and this is somewhat analogous to an SN2 reaction. We need the alkyl halide because we need this as essentially like a leaving group. And our strong nucleophile here, and also strong base, but strong nucleophile is going to be hydroxide ion. And that's going to end up substituting this halogen group here. Here, the OH minus is a nucleophile, and the bromide here, the bromine is going to react as is going to act as a leaving group, leave as a bromide ion. So we have to have 3 requirements for a nucleophilic aromatic substitution, which is denoted SNAR. So like SN, SN2, SN1. This is SNAR, an aryl substitution. So the benzene ring has to have a strong electron withdrawing group. So the ring has to be electron poor. So we want something that's essentially a deactivator for the ring. Nitro group is great. Acyl group, something like that. The ring has to possess a good leaving group, such as a halide. And the leaving group has to be positioned ortho or para to the withdrawing group. So you can see here in this example, the bromine is positioned para to the electron withdrawing nitro group. If the leaving group and the withdrawing group are meta, this reaction will not occur. The electron withdrawing group is in the meta position. It's unable to stabilize the intermediate that will be produced. And we're going to look at this mechanism here, and we're going to see that there's going to be an intermediate produced that we're going to be calling the Meisenheimer complex, which is analogous in the electrophilic aromatic substitution. We had a sigma complex. In the nucleophilic aromatic substitution, we're going to have a Meisenheimer complex, as it's called, for the intermediate. So here, let's take a look at the mechanism for how this occurs when we do, in fact, have the electron withdrawing group in a para position to the leaving group here. So notice this is going to be somewhat analogous to an SN2. It's not going to be exactly like an SN2 because the leaving group is not going to leave simultaneously upon the electrophilic attack. We're going to have an intermediate, or the nucleophilic attack, rather. So the nucleophile here is the OH group. The electrophile is the benzene ring due to the electron withdrawing effects of the nitro group, removing electron density from the ring. So we'll have a nucleophilic attack on the same carbon where we have our leaving group, the chlorine, and simultaneously, because a carbon can't have 5 bonds, we have to have the movement of these pi electrons into the unhybridized p orbital here, and we have a carbanion. And at that point, we have a allylic lone pair, so we do the allylic lone pair move, 2 arrows, 1 arrow to the neighboring carbon-carbon bond, and then 1 arrow to the neighboring carbon from the pi bond here. And then again, we have a allylic lone pair, so we have the 2 arrow mechanism for allylic lone pair. Finally, we can also here talk about, and this is kind of going backwards and undoing that and putting the electron pair here, but essentially what we're having is this electron pair making a double bond with this nitrogen, and the nitrogen can't have 5 bonds, so these electrons now go on the oxygen. That produces for us this negative oxygen. This nitrogen is making 4 bonds with no lone pair. It has a positive formal charge. And at that point, we can now describe the loss of the leaving group, which is here described with the 4 arrows. We can see here we have the reformation of this double bond, the movement of these pi bonds back here, then this movement of this pi bond here. This recovers our aromatic ring, and simultaneously the chloro group leaves. And so that produces for us our substitution with the OH group here as the nucleophile. And so this resonantly stabilized complex here with the carbanion is referred to as the Meisenheimer complex. So you can see that as a result, we have resonance stabilization through the nitro group, which is favorable and stabilizes the complex. What we're going to see is that if we have the nitro group in the meta position, this Meisenheimer complex cannot be formed. So you can take a look here. If you consider it, if we had instead the nitro group at the meta position and the nucleophilic attack occurred, we would not have the formation of this group here. So I can kind of draw this over to the side here. So notice that this occurs essentially because we can have this lone pair right here next to the nitrogen, right? And I'm just going to draw an alternative right here. We can see this stabilization occur. What we're going to see right here is that if we have the group at the meta position, when we have the nucleophilic attack of the OH group, like this, right? And then I'm just going to do this guy right here. We're going to put it right here. We get this product with the lone pair here, which is allylic. However, when we do the resonance here, we're not going to get the Meisenheimer complex because we have a allylic lone pair. The lone pair is going to go right there. It's never going to lie on the carbon that is attached to the nitrogen. And so therefore it won't be a stabilized Meisenheimer complex. And so the nitro group must be at the ortho or the para positions, the electron withdrawing group. It doesn't have to be nitro. It can be any electron withdrawing group. It has to be at the ortho para positions to produce this Meisenheimer complex. So the substituted phenol, note it will be deprotonated in basic conditions, in like with the hydroxide. So we have to follow it up, and you can see here we followed it up with the introduction of a acid afterwards to protonate the phenol, because the phenols are quite acidic, so they're much more acidic than water. So at pKa 9, whereas water is only 15.7, and so you're gonna have to add an acid to protonate that. The hydronium having a lower pKa. Now recall that we need an electron withdrawing group for this reaction to occur. This will not happen with just a halogen atom attached, because we need the aromatic ring to behave as a electrophile, not a nucleophile. It has to have a lack of electrons on the ring. So that's why we need the electron withdrawing group. So under normal conditions, this will not occur without an electron withdrawing group. We can make it occur if we have a very high temperature. We can make it occur. But these types of reaction conditions are not preferred. Imagine that you're doing this to produce a drug, a pharmaceutical drug. You want this synthesis to be as efficient as possible. And it's not efficient to get temperatures up really, really high if we can help it. So instead, what we're going to do is an alternative referred to as an elimination addition. So what we can do instead is an alternative reaction. What we can do is react the alkyl, the benzyl halide rather, with a very strong base, sodium amide here in ammonia solvent, and this will be a very, very strong nucleophile rather, and so it will attack and replace the chloro group. The regiochemical outcome here means, when we take a look at it here, the result is that if we have an electron donating group here, it's going to occur either at the ortho position, but also at the meta position to that group. So the question is, this is going on through a different mechanism. It's not going on through the nucleophilic aromatic substitution mechanism that we saw earlier, the SNAR. So what mechanism is this going through then? What's occurring here instead is we're having something that's similar to a elimination. And this was discovered by the use of isotopically labeling the carbons to figure out which carbon the amino group is attaching to. If we label the carbon here and use a carbon-14 isotope instead of a carbon-12, we can see, once the reaction is done, that not only is the amine group attached to that carbon that was attached to the halogen, but it also becomes attached to the carbon that was right next to the halogen, or in the ortho position. You'll get a 50-50 mixture. And so it is proposed that this occurs through the formation of a so-called benzene intermediate, in which, because the amide is a super strong base, it will deprotonate the hydrogen that is at the ortho position to the halogen, and then we will get a carbanion, and essentially we have the formation of a alkyne group by the loss of the leaving group here. And so this alkyne group in a benzene ring, clearly this is not completely favorable, because these would expected to be like 180 degrees, right? So clearly something else is going on here. And what's expected is that this is not a complete triple bond, but kind of partially a triple bond along the way. After this occurs, and we get the benzyne, then we have a nucleophilic attack by the amide, which then here, so we have nucleophilic attack, and now this carbon will have 5 bonds unless we move these electrons. So these electrons go in this unhybridized p orbital, and then we have also ammonia as a solvent here, so there's plenty of ammonia, and that we recover the NH2 here by the deprotonation here of the ammonia to produce another amide ion, and finally we get the installation of the amide. Now alternatively, the amide can attack at the other carbon that was not the carbon that had the halogen group, and then it can get protonated at the same carbon where the halogen group is, and then we have the installation of the amine group at the position that is ortho to where the halogen is. And this evidence tells us that this could not have occurred through a nucleophilic aromatic substitution. It must have occurred by a different mechanism. This is called the elimination-addition mechanism, because we start with an elimination, producing a triple bond from a double bond, and then an addition of the amine group. So the elimination-addition mechanism can also occur with weaker bases such as hydroxide. So the hydroxide can then do a proton transfer, giving us this carbanion here, highly unstable aryl carbanion. So we get the immediate loss of the leaving group, producing for us this benzyne intermediate. Then we have a nucleophilic attack by the OH, which again can occur on either of these carbons, producing another carbanion here, which then is protonated by water, recovering our hydroxyl group. And this is the elimination-addition mechanism. Clearly different from our other substitution mechanism because of the deprotonation that it starts with and the benzyne intermediate. So there is even more evidence for the formation of the benzyne intermediate. What was done here was the introduction of furan into a reaction in which the substituted the benzyne intermediate was produced by one of these reactions. And we know that if we have these pi bonds with the dienes, we know from chapter 16 that this can undergo a Diels-Alder cycloaddition reaction, and this produces a stable cycloadduct. And so the presence of this benzyne intermediate was confirmed by the introduction of furan into this reaction and the production of some of this cycloadduct, which indicates the presence of the benzyne as an intermediate, because this stable product was formed and then later detected. So how will we know which mechanism will occur? Will it be the electrophilic aromatic substitution, the nucleophilic aromatic substitution, or the elimination and addition? Well, first of all, you should think of the reagents. Is the reagent a nucleophile or is it an electrophile? If the reagent is an electrophile, for example, we had lots of them. The electrophiles were, for example, Br2 in the presence of the Al Br3, right? Or for the installation of the nitro group, it was a nitric acid in combination with the sulfuric acid, and so forth. We had lots and lots of electrophilic reagents. If it's an electrophilic reagent that is used, then you will have the electrophilic aromatic substitution reaction. If we have a nucleophilic reagent, and we saw two important nucleophilic reagents, these included NH2 and OH minus. These are nucleophiles here, and most importantly, you should have an electron withdrawing group on there as well. So the criteria for nucleophilic aromatic substitution are these going to be met? For example, the electron withdrawing group here, then we will have a nucleophilic aromatic substitution. However, if they are not, so here going back here, just just to go back to the nucleophilic aromatic substitution and those three conditions here. Here we have a strong electron withdrawing group, a good leaving group, position ortho or para, right? Then we can have a nucleophilic aromatic substitution. So in either case, we'd have some type of very strong nucleophile, such as the amide or the hydroxide. But for the nucleophilic aromatic substitution to occur, we must also have a electron withdrawing group. We need to have a leaving group, and it must be in the ortho or para positions. If that is not the case, then the reaction will proceed through the elimination-addition mechanism. So here is a summary of all the reactions that occurred in this chapter. We have the electrophilic aromatic substitutions and subsequent reductions or oxidations, and then the mechanism that occurs depends on how those benzene rings are substituted, right? If we have a benzene ring that has a strong nucleophile here in the presence of an electron withdrawing group and a leaving group, we will do nucleophilic aromatic substitution. However, if we don't have those conditions, for example, we have an electron donating group, or we have no electron withdrawing group at all, but we do have a strong electrophile such as hydroxide or amide, then we will have an elimination-addition reaction. And an important note is that addition and elimination-addition reaction will install groups both at the same position as the leaving group and ortho to the leaving group. And that summarizes all of the reactions for this chapter, chapter 18, with substitution reactions for benzene rings. For this week's homework, it is pretty substantial. There's a lot of practice that needs to be done to correctly determine the products and determine the direction, ortho, meta, or para direction, whether it's an electron withdrawing group, which will deactivate the ring, or electron donating group here, which will activate the ring under electrophilic aromatic substitution. This takes a lot of practice. So I've assigned a lot of practice problems. Of course, you have some that you have to turn in, some that you don't. But I think this is going to be a chapter that involves significant practice. So make sure to get that practice in as you prepare for the quiz or exams that are coming. And let me know if you have any questions. Okay, and I hope you have a great week. I'll see you next time.